This conference will now be recorded.
Hello everyone. Last day we have finished VSEPR theory, and based on that 3 problems we'll solve, and then there will be a new theory discussion which is Valence 1 theory, and related to this theory there will be 2 more topics, orbital overlap and sigma and pi bond formation. So let's start with this problem. Here some species are given in the options A, B, C, D. So we have to find which of the following are isoelectronic and isostructural. So isoelectronic, how we will understand, every atom you will consider for each of these ion. Here ion is given, though SO3 is neutral, it is not ion. So for NO3, how many valence that is how many electrons are present in N, which is simply the atomic number. So it will be 7. Then for 3 oxygen, each oxygen it is 8, so it is 3 into 8, and there is single negative charge, that is +1 you have to do. So in this way you can calculate how many electrons are present. Fine. Now once you know the number of electrons, now you are confirmed that they are isoelectronic if you find same for 2 species. So you can choose the option. But suppose in more than 2 options you are getting same number of electrons, then you have to move to the second factor, which is whether they are isostructural or not. That is, their structure will be similar type. Suppose both are trigonal planar or both are tetrahedral like this. But it is easier to calculate the number of electrons. Based on that, if you can choose only option, then you don't have to use that is don't have to apply the next one, whether it is they are isostructural or not. So here we have NO3CO3, that is nitrate ion and carbonate ion first. Now when we solve any MCQ type of question in the exam, it is always better if you can solve it as fast as possible. Now detailed, that is calculation, if I say don't do, because in both species there are 3 oxygen atoms, so obviously the number of electrons that you are getting from oxygen, it will be same, right? So what you will do, nitrogen 7 atomic number, and there is only 1 negative charge, then you don't have to do any calculation based on oxygen. Then for carbon it is 6 and there are 2 negative charge, so in both cases you are getting 8. That means these 2 will be isoelectronic. You can also add the number of electrons coming from oxygen, but if you are in hurry, you want to solve it as fast as possible, you can do it in this way. Okay, so for the first option, the 2 species, the actual calculation you can see here, NO3 minus 7 is for nitrogen, then we have 8 into 3, which is for 3 oxygen atoms, and 1 that is for the negative charge. So you are getting 32 total number of electrons. Similarly for carbonate, 6 for carbon, 8 into 3 for 3 oxygen atom, and 2 negative charge, so that is why +2, but here also it is 32. Now what about the next 3? Now for the next 3 I will suggest you don't have to do the full calculation, because number of oxygen again same, so their contribution of electrons will be same. And what about sulfur and nitrogen? For sulfur, atomic number 16, for nitrogen it is 7, and there is no negative charge here. Here you have only 1 negative charge. Now these 2 are far, that is they are differing from each other highly, so obviously they cannot be isostructural. Basically sulfur is from 3rd period and nitrogen is from 2nd period, so obviously these 2 species we cannot expect that they will be isoelectronic. So just have a look in this option, you can understand, you don't have to do the calculation, don't waste your time in doing the calculation. Then similar thing type of logic you can also apply for option C, because Cl, which is atomic number 17, same number of oxygen, so you can cancel it, 1 negative charge, and for carbon it is 6 and 2 negative charge, so obviously these 2 are differing from each other highly, so they cannot be isoelectronic. Same logic is also for D. So just based on this logic you can cancel all these options. You are left with the first option, which is that is isoelectronic. And even we don't have to consider the isostructural fact, because we have chosen the correct option. So isostructural, that factor also we don't have to consider. But if you are really curious, that is how they are isostructural, you can apply the rule that we have seen, that is steric. In the last class I have shown it. Steric number is half number of valence electron plus number of monovalent atoms attached, and plus minus charge. If it is positive charge, then you have to subtract it. If it is negative charge, you have to add it. So for NO3, it is half. Central atom is nitrogen, so it is 7. No monovalent atoms are present because oxygen, it is always there is double bond, so it is 0, and there is one negative charge, so it is 8 by 2. That is state number is 4, so it will be, yes, so it is 4. Okay, then what about carbonate? So for valence central atom is carbon, so it is 6. Then number of monovalent atoms, it is not present, so this is also giving same steric number. So when steric number is same, obviously the structure, it will be alike. Okay, so that is the reason they are also isostructural. So correct option is the first option. Next question. Based on VSEPR theory, the number of 90-degree fluorine bromine fluorine angle or angles that are present in this molecule BRF5. Fine. Options are 0, 4, 6, 8. So what you have to do based on VSEPR theory, just apply the same rule BRF5. So steric number, that will be equal to half number of valence electron. Here central atom is bromine, and bromine is from group 17. So number of valence electron will be the last digit, which is 7. Number of monovalent atoms attached, total 5, fluorine attached. It is neutral, so no question of charge. So it is 12 by 2, which is giving you 6. That means it should be octahedral, because total number of positions are 6, right? Now it is true that total number of positions 6, but how many atoms you have surrounding bromine? It is only 5. That means one position there should be a lone pair, right? If you want to do the calculation different way, that also I want to show here. So for bromine, number of valence electron 7. Out of these 7 valence electron, 5 will be used up for as bond pair. It will be engaged in bond pair. That means 2 electrons are left. So that means there will be only one lone pair. So, and total number of positions 5 plus 1, that is giving you 6. So in this way also you can do so, whatever is you are comfortable with. But ultimately the structure will be like this. So when the structure is like this, now look at this structure. If you join all these, you will be getting a square plane. But in this position, we do not have any 6 position. There is lone pair, there is no fluid. Now, suppose if it is molecule BRF6, then it is very ideal angle. That is, all the angles will be 90 degree. But in this case, this angle is 84.8 degree. And the reason is because of this lone pair, and also there are electrons present as bond pair. Okay. Now there will be repulsion between this bond pair of electron and lone pair. And because of this repulsion, all this, that is it, this square plane, it is not exactly perpendicular to this vertical bond, but it is slightly less, that is lesser than 90 degree. So geometry and shape are octahedral. That is the geometry, because ideal geometry is octahedral. It is true that one position there is lone pair, but if you consider from the point of view of 6, obviously it is octahedral geometry. But without lone pair, the remaining shape is square pyramidal, like this. This is the square, and if you join all these positions, you will be getting a square pyramidal. But this position there is a lone pair. Now because of this lone pair bond pair repulsion, the bond angles are little less than 90 degree that you expect from ideal geometry of octahedral, but here it is not ideal. So that is why number of 90 degree fluorine bromine fluorine angle, that is actually 0. So this is the correct option, option A. The molecular shapes of SF4, CF4, xenon F4. Okay, First option, it is saying that it is different. This is also different, but option C and D is saying same. Okay. And also there is further, it is saying that number of lone pairs of electron on the central atom. So sulfur is the central atom, carbon is the central atom, xenon is central. So is it 102? That is 1 for sulfur, 0 for C, and 2 for xenon, because there is respectively. Okay. The first one is for SF4, this is for CF4, and this is for XCF4. But which one is true, that we have to find. So again, we will take the help of the formula, which is okay. So for SF4, it will be half valence electron for sulfur. It is from group 16, last digit 6. Number of monovalent atoms 4, no charge, so it is 5. Similarly, if you consider CF4, now it will be half. Valence electron for carbon is 4, number of monovalent atoms attached 4, so it is giving you 4. And for xenon fluorine, xenon 8, because it is from it is noble gas, and from, if you consider group, it is 18, last digit is 8, so it is 8, 4, 12 plus 2, so it is 6. So when it is 5, we know it is total 5 position, it is TBP. When it is 4, it is tetrahedral. In short, I have written TD. And for 6, it is octahedral, OCT. Fine. Now see, even you don't have to draw the structure. As there are total 5 positions, out of these 5 positions, you have how many sulfur fluorine bond? You have total 4 sulfur fluorine bond. That means the remaining 5th position, there should be a single lone pair, right? And their structure, these 3 are obviously different structures, so these 2 obviously not possible. Now what about CF4? There are total 4 positions. All the 4 positions, there are 4 fluorine, so 0 lone pair. So 1 and 0, you have to choose between A and B, and you have already reached your answer, which is this one, because 1 and 0, you don't have to do the calculation for XZF4. Basically, once you get one lone pair and you have cancelled C and D, then also you can choose option A, because B, the first position, there is 0. So in this way, just be careful, that is so that you don't have to do the full detailed calculation, and how that is, just do it as minimum as possible so that you can reach the correct answer. In this way, you can save your time. And for xenon F4, there are total 6 positions, but out of 6 positions, there are total 4 xenon fluorine bond. So that is the reason. Rest of the 2 positions, there must be lone pair, right? So 102, and see, this is actual structure. So there is 1 lone pair, there is 0 lone pair, there are 2 lone pairs. Fine. So option A should be the correct option. So after discussing these 4 problems based on VSEPR structure determination, the next theory is valence bond theory. So remember, when we have started the chapter, the first theory, there is a simplest, that is the Lewis theory, right? Octet rule, all these things we have discussed. After that, the next theory we have seen VSEPR, and now we have reached the third one, which is valence bond theory, and obviously this is more advanced compared to VSEPR. So the problems that we have faced in VSEPR, here it is a little better theory. Okay. So Lewis' approach to chemical bonding failed to explain the formation of chemical bond. We have already seen the limitations. And also, if you consider VSEPR theory, there is also some limited applications, because when we have discussed the limitations in the last class, remember, it is mainly applicable for pre-block elements. Whatever of examples you will see, structure determination in any book, most of the examples you will see, the central atom is from p-block. You will never see any transition metal or d-block elements. That means for d-block element, this theory you cannot apply. You cannot get the correct result. So these are the limitations. Now, in order to address these issues, valence bond theory was introduced by Hitler and London, and further developed by Pauling and Slater. So what this is, this says. So start from this type of concept. Suppose there is a situation where 2 hydrogen atoms are present. One hydrogen atom is HA, another hydrogen atom HB. So we have marked it with A and B so that you can differentiate between these two. And they are separated by infinite distance. They are infinitely far from each other. So obviously there is no interaction between them. And when there is no interaction between them, the potential energy of this system you can consider as if it is zero. Now, gradually you are bringing these two atoms close to each other. They are approaching each other. So what will happen when they will approach each other? Remember, hydrogen atom, which is the simplest atom possible. If you imagine this atom, in the center there is nucleus, there is positive charge, and surrounding it there is a single electron, right? Now, if you look at this picture, you'll be seeing these two atoms. The first one HA, the second one is HB. So this is the center, and the electron is present here. This is the center for the second hydrogen, and the electron for the second hydrogen, which is HB. Now just there are three types of color for the arrows: green, purple arrow and red arrow. I will tell you to focus on purple arrow only, not green and red. So if you focus on purple arrow, what type of interaction you are seeing here? These two atoms are approaching each other. Obviously, there will be interaction between them. We will come to that point later. First of all, just focus on the purple arrow. So in addition to the electrostatic attractive force between the nucleus and its own electron. So this is own electron of HA, and there is interaction between these two. So this is the purple arrow if you follow. And similar is the case also for HB. Now in addition to this interaction, I mean to say this purple arrow, this interaction, there is also some other interaction, because this interaction within a single atom, that is also present when they are far from each other, and when you are bringing them close to each other, then also it is present. So it is present before when they are far from each other. It is also present when they are close to each other, right? Now apart from this, there is also two more interactions, and these two more interactions are basically this red one and the green one. We'll come to that in the next slide. But before that, this much information, just see. So this theory, when we talk about, basically it is based on some, we need knowledge of all these factors that you are seeing. So obviously we have to know atomic orbital. So you can see here the atomic orbital of HA, atomic orbital of HB. Then we have to also should have the knowledge of overlap criteria, how they are, these orbitals are overlapping to each other. We have to know the electronic configuration of element. So in this case, we have taken very simple atom for that is for simplicity, so that the discussion you can understand easily. But for complex higher atomic number elements, obviously electronic configuration, that knowledge also we have to know. That is how to write the electronic configuration. Remember in periodic table chapter, this we have already seen. And hybridization of atomic orbital. So this is something new that we'll also have to discuss. And the last point is mentioned, principles of variation and superposition. Now this is higher mathematics. Now valence bond theory, for your level, we do not need this type of higher mathematics. This is advanced level for the same theory, valence bond theory. But up to this, it is enough for our syllabus. Now the purple interaction that we have already seen. Next we have to know what is this green interaction and the red interaction. So the green arrows, this interaction is basically nucleus of HA. This is the nucleus of HA and valence electrons of HB. This is the valence electron for HB. So there will be some interaction. So not only there is interaction within its own electron, but when they are close to each other, this interaction, which is denoted by green arrow, that will start operating. And similarly, vice versa, nucleus of HB and valence electron of HA. So these two are green arrows interaction. And what about the red one? This red interaction is basically newly generated repulsive force. So the nucleus of HA and HB both are positively charged. So there will be some repulsion. So that is why see, the direction of the arrow is towards away from each other. It is not coming to each other, it is away from each other. So there will be some repulsion between these two positive charge and also the repulsion between the valence electron of HH. So these two newly generated repulsive force will be there. Now at the initial stage, that is when they are far from each other and gradually you are bringing them close to each other, what will happen when they are approaching each other? The attractive forces are stronger than the repulsive forces, because repulsive force can only be present when they are very close to each other. Otherwise, no question of repulsion. If the two positive charge or two negative charge of two electron, if they are close, then only the question of repulsion arises, right? But when they're just coming close to each other, not very close, obviously attractive forces will be stronger compared to repulsive forces. And in this scenario, the potential energy will decrease because attractive interactions. So when it will happen, then gradually one time will reach. So you are bringing them close to each other. First they are far from each other. Now you are bringing them close to each other. So one point will reach when the net attractive forces are exactly balanced by the repulsive forces. So when there is a particular situation, that is a particular distance, you have brought them together. Under that particular distance, this repulsive force exactly balanced by the attractive force. Then the system will reach a minimum energy. So this minimum energy, that is this distance, suppose this is the distance where minimum energy reached. So what will happen? So this is actually the bonding distance between two hydrogen atoms. Okay, so we'll see a picture related to this. So in this picture we have x-axis and y-axis, and not just x-axis and y-axis, there is also a negative scale, as you can see. So in the y-axis, potential energy is present in kilojoule per mole unit, but we have considered the negative side of it. So this is 0, this side is positive, this side is negative. So all these values are negative, minus 100. So if it is minus 100, obviously somewhere here it will be plus 100. So minus 100, minus 200, in this way it is increasing downward, but with a negative value. And what is in the x-axis? X-axis is basically internuclear distance in picometer. That is the distance between two atoms. It is very short distance. That is why it is in picometer unit. Now look at this point 1 when they are far from each other. Okay, and this is the corresponding energy. So this is position number 1. Next come to position number 2. Now they are slightly close to each other. So attractive interaction will start operating. Then come to position number 3 when it is further closed. Now this is the bonding distance. Okay, so if you draw a line at the corresponding, this is the position. If you draw a line here, this is the position for x-axis. Look at the value, it is 74 picometer. That means this is the bond length of hydrogen, right? And here the corresponding energy is somewhere here. This is the peak point, minimum energy. If you look at this maroon line, which is the line for potential energy, when you are bringing close to each other, it is in decreasing. Then it is the minimum point, that is the minimum energy value, which is minus 432 kilojoule per mole. So what is happening? One by one we have to see. The atoms HAHB, they are now said to be bonded together by a covalent bond and have maximum overlap between the atomic orbitals. So it is talking about position 3, the first statement. And the internuclear distance at this stage 74 picometer, which is actually the HH bond length of hydrogen. And the corresponding energy, as it is negative sign, so obviously it is liberated energy. Energy is liberated, 436 kilojoule per mole, and this is actually the bond energy. So if you break the bond between two hydrogen atoms, this amount of energy will be liberated. Okay. Now since the energy is released during the bond formation, the resultant molecule is stable. Because when you are breaking a stable system, you are disturbing a stable system, obviously energy is liberated. So this much of energy it is already present in the molecule, and when you are breaking it, this amount of energy is liberated. That means originally, before the breaking of the bond, originally the system was very stable. That is the proof. As the energy is liberated, you are not that is this much of amount of energy, it is liberated. We are not providing it, it is liberated. Fine. So the next point is we have reached from 1 to 3 to 1 to 2 to 3. Now what about after 3 you are further bringing them close to each other? That is position number 4. So if the distance between the two atoms is decreased further means beyond 74 picometer, now repulsive force will dominate over attractive force. Up to 0.3 is the 0.3 is such a point where these two forces are balancing each other. But when you have crossed this point, you have reached 4 position. Now repulsive forces will be dominating force compared to attractive force. That is the reason. Now from this minima, energy is again increasing. See, from minus 432 it is becoming, then minus 400, then minus 700, and then the more close it is. So basically you are moving in this direction. So R is gradually decreasing when you are moving from right hand side to left hand side. In the x-axis, that means internuclear distance is gradually decreasing. So when it is very, very low value, if you draw a line corresponding energy, now it is becoming positive, around plus 100. Okay. So in this way, you can understand how two isolated hydrogen atoms, when they are far from each other, then you are bringing them close to each other, and gradually one situation will reach where bond formation will take place. At this position, two different types of forces, repulsive force and attractive force, these two will be balancing each other. So here if we look at this equation, if H2 is there, yes, H2 is there, and we are providing this much of energy because this bond is already stable. We have to break this stable bond. Then you are getting two isolated systems. So this is a stable situation, and in the right hand side there is unstable situation. But if you consider the opposite process, that is from isolated condition, now you are moving to H2. In that case, that is if you follow the process reverse direction, in that case it is liberated energy. But if you move from left hand side to right hand side, that is already H2 is there, it is stable, and you are disturbing this stable system, then you have to provide energy. But if you consider the reverse process from isolated hydrogen atoms, you are making H2 molecule. So obviously it is a stable situation we are reaching. So that is why amount of energy will be liberated. Okay. So it is 435 point is close to 436. So next, based on this picture, whatever discussion we have done, this problem is based on that. Intermolecular potential energy for the molecules A, B, C, D given below. Basically, these are atoms, not molecules. Okay, just make the correction. For suppose there are total 4 different elements are present, A, B, C, and D. Now from this diagram, where you can see in the y-axis there is potential energy in kilojoule per mole, all the values are negative, and here we have interatomic distance, the distance between two atoms. So for AA, that is two same atoms AA, this is the curve. The nature of the curve is always like this. It is a common pattern you will observe, but sometimes it may be narrower. As you can see, for AB it is narrow, for AD it is very broad, for AC it is something intermediate, right? So it may vary, but common pattern will always more or less it will be same. So what statements are there? D is more electronegative than other atoms. That is compared to ABC, it is more electronegative. And basically 4 statements are there. We have to choose any one statement which is correct. Then the second statement, AD, that is AD bond between A atom and B atom, has the shortest bond length. Okay. Then third statement, AB, in case of AB bond, that is the stiffest bond, that is tight bond, stable bond, and A, largest bond enthalpy. Bond enthalpy means, remember in the last slide, what is the bond enthalpy? That is bond energy for hydrogen. It is around 436, right? So same thing it is saying that in which case bond enthalpy high, it is saying that it is maximum for AA. Now, if the first statement, whether it is true or not, B is more electronegative, how to understand that? See, as there is only AD bond is mentioned in the picture, there is no bond like CD or BD. So, if there is bond that is for potential energy diagram, one is for AD, then BD, then CD, then only you can compare whether D is more electronegative or not. But here we have only AA, AB, AC, AD. So directly from this picture we cannot say, we cannot predict it. Come to the other statement, AD has the shortest bond length. Now this you can easily understand from the picture. This is the minimum energy point. So if you draw a line here, it is crossing at the point 150. Okay. For AC, it is crossing somewhere between 100 and 150. For AB, it is slightly lesser than 100. For AA, it is slightly greater than 50. So obviously, AD has shortest bond length. This cannot be true. The bond length for AD, which is, you have to draw a line at the minimum, there is a peak position, energy minima. From that point, you have to draw a straight line, which is cutting the X. So it is cutting at 150. So it cannot have shortest bond length. Basically, it is having longest bond. So this cannot be correct option. Then AB has stiffest bond. Now for AB, the energy minima, that is maximum. Why I am saying so? This is the minima for AA. If you draw a line, it is somewhere between minus 400 and minus 500. For AB, it is greater than 5 minus 500. For AC, it is lesser than minus 1. For AD, it is somewhere here. If you just draw a line from this minimum. So for AB, it is maximum minimum energy, right? So it means it will have the stiffest bond, because when it is the more minima, it is more negative is the energy, potential energy value corresponding to this minima peak point, the more will be the stable bond or stiffest bond, that is tight bond, very stable bond. So these should be the correct option. And the last statement is saying that AA has the largest bond enthalpy. Now bond enthalpy, obviously, see, I have just drawn from, this is the minimum point. Let me use another color. So this is a minima for AA. If you draw a line, it will be cutting between minus 400 to minus. So largest bond enthalpy is basically for AB, not A. That is also not correct. So potential energy for AB molecule is minima, that is largest bond enthalpy, you can say, the most stable bond, the strongest bond among these three, and it is also the stiffest bond, that is the shortest bond. And obviously bond enthalpy large, that I have already shown. And B is most electronegative, because with B, A is common here, right? So keeping A common, if we compare with its interaction with B, C and D, A is common, you are comparing its interaction with B, C and D. So in which case A is common, in which case energy minima you are reaching, in which case you are reaching the stable bond, it is for AB. That means the electronegativity difference, because A is fixed, so electronegativity difference in case of A and B system, that is basically maximum. So that is why the more is the difference in electronegativity between A and B, they will be attracted to each other and the bond will be very stable compared to AC and AD. Okay, because in system D, Basically, this electronegativity that we are comparing, that is between B, C and D. So for D, as here energy minima, it is around, it is least negative. So that means the interaction between A and D, and bond length is also very high. That means difference of electronegativity between these two, it is not so high. It is maximum in case of this one. So that is why their bond between A and B is so tight. Right? So this is the correct option. So in valence bond theory, we should have the knowledge of orbital overlap. Remember, these points are mentioned in the black box in the slide where first BBT theory is mentioned. So one is orbital overlap, then we also have to know sigma bond, pi bond, hybridization, all these facts one by one. So orbital overlap concept. Again, we will take hydrogen molecule because it is simple molecule. So in the formation of H2 molecule, we have seen there is a minimum energy state where two hydrogen atoms are close to each other, are so close that their atomic orbitals, there is some partial interpenetration. So this is isolated HA, isolated HB, but when they are bonding distance, what will happen? There will be some overlapping zone. So this is the overlapping zone. That means the electron atomic orbital means what? This is the electron density, right? So electron density of HA. Now there is some interpenetration. It is no longer isolated. There is some merging area. So this partial merging of atomic orbitals, that is actually known as overlapping. And this type of overlapping, it results in the pairing of electron. We know that when there is bond formation, one electron, there is another electron, and when they will pair up, their direction will change like this. Okay. So this is pairing of electron in the overlapping zone. So when half-filled orbitals of two atoms overlap, a covalent bond will be formed between them. The strength of a covalent bond, that depends upon the extent of overlap. How much overlap is present? More overlap means more strong bond. Less overlap, less strong bonds. Each atomic orbital has a specific direction except s orbital, which is spherical. So s orbital is spherical. So no question of direction, we can say, for s orbital. But if you consider p orbital or d orbital, then direction, you can say there is specific direction. So orbital overlap takes place in the direction that maximizes the overlap. Read the sentence again. Each atomic orbital has a specific direction, and hence orbital overlap takes place in the direction, only in that direction where maximum overlap is possible, because our purpose is to get maximum overlap. Okay, though for s orbital it is not applicable because it is similar, that is electron density is spherical. But for p, it is and in particular direction electron density is high. For d also same thing. So here these two hydrogen atoms, this is the A, this is B, and see when there is, this is the overlapping zone, and these two electrons, they are opposite direction. So according to orbital overlap concept, atoms combine by overlapping their orbital and thus forming a lower energy state where their valence electrons with opposite spin pair up, and ultimately there is formation of covalent bond. So in this case, we are getting a covalent bond between two hydrogen atoms. Next, we will see. So here you can, in this picture, as hydrogen, there is only one s orbital. So we can see the orbital overlap between two 1s. This is the overlapping part. But what about if you have 1s, 1p, or if you have 2p, or it may be 1p, 1d, like different types of combinations are possible. But before that, we have to know what is different types of overlap. That is positive overlap, negative overlap, and also there is another term which is known as zero overlap. So when orbitals of two atoms come close to form bonds, their overlap It may be 3 types. Though mostly it is positive and negative, 0 is special case, but these are the 3 possibilities, and that depends on whether when they are overlapping, then overlapping that is atomic, what is the phase sign. So here you can see in this picture there is some positive sign, there is some negative sign. So all these signs, don't think these are the positive or negative charge. Don't make that mistake. It is basically the phase sign, right? Now it depends on in which sign they are interacting and also the direction of orientation. So let's see what is positive overlap. So here we have 2pz, and this 2pz, suppose as it is pz, that means it will be in the z axis, lying on the z axis, and the 2 positive phase which is in blue color and the negative phase that is in black color, the 2 blue part, they are coming close to each other. So this is the overlapping zone, and there will be formation of a bond. Now if this black one is orienting towards another pz, that is plus and minus, this is negative overlap, so phase sign must match. Then if you have taken one pz and one s, now for s it is only a single charge possible, it is spherical, so positive positive. But if we have, that is just change the sign, now the black one is right hand side, the blue one in the left hand side. So in this case now the negative is overlapping with the positive s, so that is what is negative overlap. Then we have this lateral overlap of 2px. Now why it is px? Because this is the z axis where you have this pz line. So obviously if pz, this is the z axis, px will be perpendicular to it. Now when they are laterally approaching each other, these bonds are called basically pi bond. It is not head overlap, we will come to that point. But right now just focus on the fact that 2 similar phase sign, so that is why it is positive overlap, but this is negative overlap. Then we have taken 2py. So if you consider x-axis, y-axis, z-axis, this is z, as you can see, horizontal, this is x. Now both these are present on the screen of the laptop, and this dotted line, it is as if y. So this is also 90 degree, all are 90 degree to each other, x, y, z axis. So this is far away from us, right? So that is why it is drawn in this way. See, it is not exactly vertical, it is like this. Px will be exact vertical, Pz will be exact horizontal, but Py will be like this. But it is same phase sign, so it is positive, another possibility negative. Now in some cases zero overlap is possible, as you can see, if you have px and s. Now just compare, that is if s as if it is coming in the middle position, but in the middle position there is no electron density, no dispersion, right? So this is a kind of zero overlap, because you cannot say there is any direct interaction between two positive or one positive, one negative, or two negative, no. And then if you have taken px and py, no direct interaction is possible, so this is also zero overlap. So positive overlap of atomic orbitals, when phases of two interacting orbitals same, then overlap is positive, and in this case only bond formation possible. If it is negative overlap, bond formation not possible. When the phase sign between two is opposite, overlap is negative, bond formation not possible. And when orientation of two interacting atomic is such that there is no overlapping possible, no overlapping, no question of overlap. If overlapping is taking place, then only the question of negative or positive takes place. But if there is no overlapping, then you will be calling it zero overlap, right? Now sigma and pi bond, though you have already seen sigma and pi bond. The first two picture is basically sigma bond. The next two picture is basically pi bond. But we will see how it is. Based on the nature of overlap, when they are approaching to each other orbitals, then depending on that, covalent bonding That may be sigma bond or it may be pi bond. So when two atomic orbitals overlap linearly along the axis, that means it's like this, along. If this is the axis, they are lying on the axis, not perpendicular to the axis. In this case, the bond will be sigma bond. It is also known as axial overlap, or you can call it head-on overlap. So it is also possible between 1s and 1p. Overlapping involving an s orbital, that is involving s orbital means it may be that's only one of them is s, or it may be both of them is. So if that is the case, involving s, both s or either one of them is, that will always result in sigma bond because it is spherical. So lateral overlap for s is not possible. So SSSP, it will always be only sigma bond. So here we have taken the molecule HF. So HF, hydrogen has only one s, but for F there is p orbital present. So we have taken z axis. We have chosen pz, not py or px. So in this case, you can also see x and y axis, but we have chosen for sigma bond formation z axis. So here sp overlapping is taking place, 1s and 1p. But the important point is this is sigma. Then overlap between two p orbitals along the molecular axis, that will also be sigma bond. So SS you have already seen. In case of, remember, two hydrogen atom, we have already seen how SS. So this is always sigma. Then right now you have seen 1s and 1p. Next you will see 2p. So for fluorine molecule, there is 2 fluorine. So we have considered 2p. It may be, you can choose z axis, y or x, whatever it is. But it is lying on the axis. So suppose if I am writing z here, this axis must be z axis. So this is pp overlap. This is sigma bond. Fine. Now what about pi bond? When two atomic orbitals overlap sidewise or lateral, the resultant covalent bond is called pi bond, which is denoted by this type of sign. Now remember one thing very important, sigma bond compared to pi bonds, they are always more strong. And the reason is extent of overlap in case of sigma is always high. And more overlap means more strength of the bond, right? So this is SS sigma, this is SP sigma, this is P sigma. Now you will see pi bond. So suppose this is z axis. So obviously it will be x and this will be u. So suppose here we have taken 2px and there is lateral overlap or sidewise overlap. They are not facing each other. They are coming close to each other sidewise. So that is, it is p pi bond. That is pi bond between two p orbit. It may be also possible between 1p and 1d. Okay, and between 2d. One difference between single and multiple bond. Single bond means there is only one bond. Suppose you have any CC single bond, but multiple bond means like this, double bond or triple bond. Now when if you compare these two, single and multiple bond, double or triple, single bonds only have sigma bond. So when you have any sigma bond between two atoms, not necessarily CC, here I have taken CC, so it is always sigma. It is not that there is a single bond, it is pi. That is not, that is rare case, very rare. So it is always sigma. But multiple bonds, when you have one of them will be sigma and rest of the two in triple is pi, and here the remaining one is pi in case of double bond. Okay. So in CC triple bond there is one sigma and 2 pi. There is one sigma and 1 pi in case of CC double bond. In case of CC single bond, there is single sigma. So here we have z axis. So in z axis, obviously this orbital is pz. So as if it is two oxygen atoms, we have taken 2pz, and you know oxygen atom there is a double bond. So one is sigma, another one is pi. So sigma bond between two oxygen. This is a head-on overlap. This is sigma bond. But there is also pi bond. So this is px. This is also px. Here z-axis is the molecular axis. What is the meaning of molecular axis? That axis where the sigma bond is formed. So in question, this type of term you will be seeing, it is very common. It will be mentioned in the problem that consider z-axis as the molecular axis or consider x-axis as the molecular axis. So what it means? It means the sigma bond, the head-on overlap, that will be based on z-axis or x-axis as it is mentioned. So as here molecular axis is pz and there is sigma bond formation by head-on overlap between two pz. So obviously the pi bond will be either between two px or two py. So here I have written px. So this is sidewise overlap. So as you can see, overlap is compared to sigma overlap, quantity is less, extent of overlap is less. So that is why pi bonds are always weak. Okay. So in this way, z-axis is a molecular axis here. So pz overlap, that will generate sigma bond, but between two px, or you can also take two py, there will be lateral overlap or sidewise overlap. So that is why this is pi bond. So in this way, between two oxygen atoms, one bond is sigma, another bond is pi. So in this picture, you can see both of them together. Okay. So here we have problem. Match the orbital overlap figures that is shown in first column list 1 with the description given in the list 2. So in list 1, you have different types of interactions given, and there is some names given, that is what type of bonding is there. Basically, you can see here bonding and anti-bonding is mentioned. So when there is phase sign is not matching, suppose one is positive and other one is negative, in that case you can call it anti-bonding. Remember, when we have seen bonding and anti-bonding, what is mentioned? Only when it is positive overlap, then only bond formation is possible. But if it is negative overlap, bond formation is not possible. Just have a look in this slide. So here what is mentioned, that overlap is negative, no bond formation possible. Here only bond formation possible. So that is actually bonding and anti-bonding, two possibilities. So first picture, it is between 2d orbital, isn't it? So 2d orbital, that is mentioned, and it is also bonding between, because phase sign is matching. Here positive negative, that is not written, but you can see it from the color. So one is white, another one is gray. So two white is approaching each other. So it is between 2d, and obviously it will be the correct. It is matching fully. So A should be R. Then B, it is 1p and 1d, but it is sidewise overlap. Okay. So P and D, it is sidewise. But see, even if whether it is pi or anti, even if you don't go to that point further, then also you can choose the correct option, because it is P and D, that is clear from the picture, and P and D is present only in point P in list 2. So B must be matching with P. And how, why it is P and D, that is fine. It is sidewise, that is why it is pi. And it is anti-bonding because phase is not matching. It is white, it is gray. It is gray, it is white. That means phase signs are not matching. Then what about C? C is basically, it is spherical, so it is S, and this is P, and there is sigma bond formation, because when there is S, obviously it has to be sigma. C is matching with Q, and the last one is again sigma. Phase signs are not matching, so it will be anti-bonding, and it is between two P. So it is only remaining PP sigma, as well as it is anti-bonding. So from this, to solve this problem, we'll be getting all the ideas clear, not just between what orbitals the bonding is taking place, B, P, D or S, that also you can understand. Whether it is pi or sigma, that also you can understand if you solve this problem correctly. And whether it is bonding or anti-bonding, that is positive overlap or negative overlap, that also you can understand. Okay, so A is R, B is P, C is Q, D is S. So A and R, that is in option 1 and 2. So you can cancel these two if you are sure about that. But the next one is also same. Okay, so you also have to move further. So considering all this one is matching with the correct answer, right? This is the correct answer. Now, after finishing this theory, the next concept is hybridization. Now, hybridization is also under VBT. Remember, in VBT, the first slide is mentioned, we should have knowledge about some terms, that is atomic, orbital overlap, then electronic configuration, that you already know. In other unit we have learned it. And what about hybridization? So it is completely another topic. I will not start it today because we will not be able to finish it. We will start it freshly in the next class. Okay, so we are ending here. Thank you for listening.